Today on Applied Science, we're going to take a look at the process of improving drill bits by dipping them in liquid nitrogen, a process known as cryogenic treatment. So I'm going to show you how I did this in the shop here, and then also how I tested it, and then we'll also use the scanning electron microscope to take a look at the microstructure to try to figure out what's actually happening during this cryogenic treatment process. But the video actually starts in an unusual location, actually in the driveway. I've owned this DeLorean for quite a few years, and one of its many weird quirks and features is the doors are opened by a torsion bar. There's a gas strut to hold the door open, but the thing that actually starts the door opening is this torsion bar, which is said to be cryogenically treated. And the reason that's needed is because this bar has to go through a 90-degree twist every time you open the door, and it has to withstand, many thousands of these cycles. So I started researching why you would ever want to cryogenically treat a piece of steel and what you actually get out of it. Does it actually make it stronger? Does it actually make it tougher? Like, what are you actually getting out of it? So instead of experimenting on my car, I figured a good way to test this out would be to use drill bits. So the idea is buy a whole bunch of drill bits, all the same. These are 1/4 inch diameter stub length from McMaster. And then cryo-treat half of them and leave half of them untreated and just start drilling a bunch of holes and count up how many holes we get for each bit type before they break. And the results are truly staggering. So the untreated bits with this machining setup, I averaged 32 holes per bit before it failed. And then with the cryo-treated bits, I got 60 holes before the drill bit failed. So a huge difference. I thought there might have been a systemic problem in my testing, or maybe I was doing something else. But as it turns out, I'll link to some research papers that have very similar performance gains listed to what I got. Almost a doubling in drill bit life just with this cryo treatment process. I should add that this is a pretty intense machining setup. So we're running at 131 feet per minute, which is like 40 meters per minute. And we're drilling into mild steel. And I mentioned the diameter is about 1/4 inch or 6 millimeters, and the depth of the hole is 3 diameters. But initially, I started off with this setup, 30 meters per minute being the only change, 0.1 millimeters per rev, or 0.004 of an inch per rev. But I actually got all of these holes out of this single bit, and it was still cutting at the end. So the trick is that the surface speed makes a big difference, and I just can't test a sort of more normal surface speed because I don't have as much steel to go through. So if I were to test this one with cryo and regular, I would need, a 4x8 foot of steel, a sheet of steel to test all this out. So anyway, I went to a much more aggressive machining setup so that the bits would in fact fail faster. The failure criteria that I used for this was done by sound. And I realize this is somewhat subjective, but when I started testing, I found out that measuring whether a drill bit is really at its end of life or not is actually pretty subjective itself, right? I mean, you can always keep pushing it until the thing actually just physically breaks into 2 pieces. But that's kind of a little too aggressive for what I'm doing. So based on my experience machining things, I would listen to the sound of the operation, and any sort of cracking or serious spindle, lowering of RPM because of the load was considered a failure. And I'll play some examples for it so you can hear what a failure sounds like. I realized halfway through that I should have blinded myself. So what I was set out doing was just going back and forth. So untreated cryo, and so on. And then halfway through I realized, boy, that was dumb. Since it's a subjective failure criteria, I can't be aware of what it is, or I'm contaminating it. So then halfway through, I marked the bottom of each bit and then put them into the bucket and then opened the top of the bucket so I couldn't see the bottoms of it, took a bit out and then tested it, and then continued on with the results. So I did not know, in fact, which bit was which after this point. It didn't make any difference. I mean, the differences are so huge, for example, between this untreated bit getting 23 holes and this cryo bit getting 84 holes. It definitely was not a close call, let's just say. Pretty dramatic difference. Let's talk about the cryo process itself. It's actually pretty easy. You just take the bits, cool them down slowly to liquid nitrogen temperatures, hold them there for about 20 or 30 hours, and then warm them up slowly, and that's it. Couldn't be much easier. So lucky me, I actually have a cryo cooler that generates liquid nitrogen on demand. So I took the bits and put them into a little foil pack with a temperature probe and put them into a vacuum flask, and then put this cryo cooler on top and used a variac to power up the cryo cooler slowly. So eventually this cryo cooler uses about 150 watts and will drip liquid nitrogen off the end of it and down into the flask. I have a video on my liquid nitrogen generator if you want more details on this. If you don't have access to a cryo cooler, heaven forbid, and you're starting with basically a tank of liquid nitrogen, what you want to do is drip it slowly into the thermos so that you don't thermally shock the steel. I get the feeling that this is actually not a huge concern, and you could probably just pour it in kind of slowly so that the liquid nitrogen cools the thermos down a bit, and then pour in a little bit more later or whatever. I didn't experiment with trying to break the steel due to thermal shock, but all of the information on the internet claims you have to cool it down and warm it up slowly. And I'm using this PAX Instruments thermal logger, which works really well, except at liquid nitrogen temperatures. It reads a little low. So you can see on the graph here that my cool down period was about an hour, and that's correct. But the ultimate temperature couldn't possibly have been negative 240, because that's much colder than liquid nitrogen. It should have been about negative 200. But anyway, it shows kind of the ramp down and the ramp up that's realistic. Also, one of the research papers that I linked to in the description claims that you have to temper the steel after the cryo treatment process. So after it comes out of the cold and comes up to room temperature, you're supposed to bring it up to 300 or 400 C and then back to room temperature and then back up to 300 or 400 C a few times to temper it. Another paper that I found didn't mention this at all, and I didn't do it either. I don't really see the point of that, because tempering steel is meant to convert some of this very hard substance to a less hard substance within the steel, and the whole point of the cryo treatment is to convert everything to this completely hard state, right? So I don't really understand even why that would work, but since we're talking about steel structures, let's talk about what actually is happening in this cryo process. Recall that when you want to harden a piece of steel, provided it has enough carbon content, about over 0.4 or 0.5%, the way you do it is heat up the piece of steel to red heat and then quickly quench it. And rapidly cooling it is what causes this crystalline structure to form that's really hard. It's not very tough, it's actually very brittle, but it is very hard. And I have a whole video on steel hardening if you're interested in that. So this chart here shows the process happening. You basically start off up here with a red hot piece of steel, and if you cool it down really quickly by dunking it in water or oil, for example, you end up with this really hard crystalline structure called martensite. That's what the M means. And the graph shows martensite starting to form at about 220 degrees C, and they claim 90% will be converted to martensite at 120 degrees C about. But the graph actually keeps going. And so the first sort of, obvious attempt at understanding this cryo treatment is that, well, it's colder, and so if we're only getting up to 90% converted at 110 degrees C or 120 C, if we're down at negative 200 degrees C, we've got to be closer to 100% because it's going up as we go down. And so, at first it seems weird because this drill bit was made, months or years ago, and it's been sitting on the shelf, and then it was shipped to me, and then I put it in the liquid nitrogen. It seems like that length of time would sort of erase any ability to affect its heat treatment. But actually, as it turns out, no, it's still changing. The steel is still able to be modified by temperature. And you can see on the graph the time is actually logarithmic. So we could be out at 10 to the 8th seconds or whatever, and you can still get it colder and still convert more of the structure to martensite. So basically, what's happening is we're just finishing off the heat treatment even after the steel has been tempered, which is interesting. So tempering is the process of converting some of this martensite to the slightly softer form called perlite. And the reason you'd want to do that is so that your drill bits don't shatter the first time you use them. You want this thing to be really hard, but also it needs to give enough so that if this thing hits a little, an uneven spot on the surface, it doesn't just chip the tip off. And deciding sort of how tough and how hard the material needs to be is a good trade-off that tool makers have been doing for ages. But the trick is that if you really do want to convert everything possible to martensite, and then you give it a certain amount of temper, you can then later go back and still convert more to martensite. And that's what this cryo process is doing. So, you know, theory is great and all, but what's even better is seeing the change with our own eyes. So what I wanted to do is take one of the treated drill bits and one of the untreated drill bits and make one of those really cool crystallographic images that you've seen, maybe from metallurgical textbooks or whatever. And I've always wondered how to make these things. You know, it's not obvious, right? You can't just put a piece of metal under the microscope and see this beautiful crystal structure. There has to be a couple things that happen. One, you have to polish the surface of the metal to an absolutely great degree, right? Because the structures that we're looking at are only tens or hundreds of microns big. So if the surface is scratched, even with, you know, tens of microns level of scratches, you won't really see any of the structure. So that's one step. Then you have to etch the metal with a special etchant so that only the certain regions are etched that you want to see, right? Like you need contrast. If the etching just applied everything to the same, you know, applied equally to the whole surface would just move down, you wouldn't see anything. So we need an etchant that preferentially attacks certain structures over others. And then we have to put it into a microscope where the light comes from the top. So most biological microscopes like this one work by shooting the light up from the bottom, or occasionally you can kind of aim it in from the side like this. But it doesn't work for getting these really nice crystallographic images because the light has to be coming exactly on axis with the viewing angle, or otherwise this effect doesn't work where you're looking at the very tiny differences in surface quality. So I hacked together this really cheesy setup. It's basically just a piece of plastic that I actually used in another experiment, my Raman spectrometer, and it's just a piece of plastic with a beam splitter here. And I put this on and shined some light in here and then put the camera on top and was actually able to get a not bad result. However, what we're looking at here is a piece of low carbon steel that has been normalized or heated up and then cooled down at a relatively slow rate. So the crystals are big. The magnification here is, you know, on the order of 100 or 200x. And these crystals are relatively huge. For the crystals in the drill bits, the size is down in the tens of microns, and I just can't image it with this microscope. The light microscope with my setup is just not powerful enough to see it. But lucky for us, I have a scanning electron microscope that can go to much higher magnifications. The special etchant that I'm using is called Nital for nitrogen alcohol, and it's made by starting off with methanol or ethanol and adding to it about 5% by mass nitric acid. And this one is actually fairly dangerous. Nitric acid is a strong oxidizer, and you're basically adding it right to a bunch of fuel, the alcohol. So it's very important that we don't exceed 5% by weight nitric acid. There are some confirmed stories on the internet of really bad explosions that happened, I guess because someone capped the bottle and it outgassed, or maybe the thing just exploded outright. But anyway, if you're mixing this up, be very aware that this is in fact a potentially explosive mixture. The etching process is very quick. I used about 2 minutes to etch this tool steel, and that seemed to work just fine. For softer steels like low carbon steel, even 5 or 10 seconds in this 5% Nital is enough. So I made my samples by putting them into a little tub with some epoxy, sanding it down, and then going up through the grits all the way to these really fine polishing papers. It's actually a cloth coated with really fine abrasive, like 0.5 micron abrasive or something. And you end up with this mirror finish, crazy polished kind of thing. It doesn't have to be super flat. In fact, mine are not, because the epoxy is so much softer than the metal itself. It kind of mounds up a little bit. So the surface isn't crazy flat, but it is locally flat. It's very smooth. And I loaded these up into the scanning electron microscope, and lo and behold, there is a difference. Again, I thought the difference was so shocking that something might have gone wrong. And so if you look carefully, you can see there's these grain structures pretty well defined in the untreated bit. And then in the treated bit, it's completely flat. Like there's no surface features that look like grain boundaries. The white dots are very likely carbide precipitates. So I mentioned that you need at least 0.5% carbon in the steel to harden it, and a lot of that carbon forms these little hard particles that kind of hold the matrix together, right? It's kind of like concrete and cement. The strength of the material comes from the little rocks in it, and the cement itself is okay in strength, but it's really the rocks that give it the ability to be abrasion resistant. Same thing with this steel. These carbide precipitates are important for keeping the steel very strong. Additionally, these drill bits are made from high-speed steel, which has molybdenum and chromium in there, which also forms carbides, like chromium carbide, molybdenum carbide. And those are especially good. Those are like really hard rocks to really hold the thing together. So anyway, the carbides seem like they're about the same, treated versus untreated. But certainly this grain boundary missing thing is weird. And again, I went online to see if this result is known, and actually did find a couple papers that looked kind of like my results. Cryo-treating it basically, the martensite basically forms into itself. Like the boundary is almost eliminated because the conversion to martensite is more complete. At least that's my understanding of this. So this seems like a no-brainer process. Like, why wouldn't you just cryo-treat all pieces of steel? Well, remember that there is no free lunch. So if we're making the steel harder or more wear-resistant, it's very likely that we're making it more brittle as well. The change is not huge. I mean, we're not making it twice as hard or anything, so we wouldn't expect a huge change in fracture toughness or brittleness, but it will be there. And depending what kind of a tool you're making, you may not really want the absolute hardest tool. Like with the drill bit, for example, this is actually a good one. You know that people are going to put this in a hand drill and lean on it back and forth like this, and they might snap the drill off. So you want it to have a little bit of give. You don't want it to be as hard as you can make it. And it's possible that the manufacturers have sort of optimized this drill bit to be flexible enough so that people don't break them when they're using them, but hard enough so that it wears well and gives overall good performance. If you kind of know what you're doing and you have a CNC machine or a machine shop and you know you're going to use the drill bit in a very controlled way over and over, yeah, go for the hardest one. In fact, they make solid carbide drills that are basically that. Also, if you search around, you'll find plenty of manufacturers are selling cryo-treated drill bits as like their selling point. But generally, these are coming from companies that don't make tools for professionals. They're generally selling to the home user market, and the banner of cryo-treated is kind of an exciting thing, but the performance gained by it is maybe not as important to the home user. So anyway, cryogenic treatment of steel is something that I've wondered about for years, and so I actually have a great time making these videos because I get to answer questions that I've had for a long time, and hopefully it answers questions that you've had for a long time too. So I hope you found that interesting, and I will see you next time. Bye.